Hello everyone, my name is Santosh and I am a student of Chemistry Honours first year. Here is an audio video lecture on substitution and elimination reaction. Types of nucleophilic aliphatic substitution are first order and second order reaction. We have learned that alkyl halides undergo a variety of nucleophilic substitution reactions. It is interesting to note, however, that all nucleophilic substitution reactions do not take place by the same mechanism. On the other hand, there are two different mechanisms possible for nucleophilic aliphatic substitution. These are bimolecular nucleophilic substitution, that is SN2, and unimolecular nucleophilic substitution, that is SN1. Let us illustrate these mechanisms by considering the hydrolysis of an alkyl halide by hydroxyl ions. Bimolecular nucleophilic substitution SN2, where S stands for substitution, N for nucleophilic and 2 for bimolecular. According to this mechanism, the reaction is believed to take place by a concreted process involving a single step. Attack of hydroxyl ion or any other nucleophilic reagents takes place simultaneously with the loss of halide ion, that is, the bond between carbon and hydroxyl ion is being formed at the same time that carbon halogen bond is being broken. OH negative plus Rx will raise to ROH plus X negative. This means that the rate of reaction should depend on the concentration of both the reagents. As such, the rate of the reaction may be expressed as R is equals to K Rx concentration into OH concentration. Since the rate of formation of alcohol is found to be proportional to the concentration of both alkyl halide and hydroxyl ion, the reaction is said to be follow the second order kinetics. A single step nucleophilic substitution reaction of this type, which proceeds by simultaneous collisions of two particles, is known as bimolecular nucleophilic substitution or SN2 reaction. A simple and prominent sample of SN2 substitution is provided by the hydrolysis of methyl bromide by hydroxyl ions in the aqueous solution. It may be noted that the hydroxyl ion attacks the carbon on the side opposite to bromine, because the attacking nucleophile cannot approach the methyl bromide molecule from any other side due to the repulsion of the negatively polarized bromine. This is referred to as backside attack and is supported by stereochemical evidence. As the hydroxyl ion approaches the carbon atom from the backside, a transition state is reached in which there is a partial formation of COH bond and at the same time a partial breaking of CBr bond. The central carbon atom in the transition state acquires sp2 hybridization. As the electrons on the hydroxyl ions begin to be shared by carbon, the negatively charged on the hydroxyl ion decreases. Similarly, bromine develops a partial negative charge as it partially removes the pair of electrons shared with the carbon. The transition state is quickly transformed into the final products, that is methyl alcohol and bromide ion. Since the formation of transition state involves collision between two particles, the reaction is obviously bimolecular. This is confirmed by the fact that the rate of reaction depends upon the concentration of both the hydroxyl ion and the methyl bromide in accordance with the rate Q. The energy profile diagram of the reaction is shown here, where the energy of reactant OH negative plus CH3Br is high, while the energy of CH3OH plus Br negative, that is product, is low, and the transition state is CH3Br negative OH negative, which is a partial bond. Stereochemistry of SN2 reactions. The postulations of backside attack by the nucleophilic reagent is SN2 reaction requires that the configuration of the product should be opposite to that of the reactant. This has been found to be so in actual practice and can be clearly shown by considering the alkaline hydrolysis of optical active 2-bromo-octane, that is CH3CHBr C6H13. It should be worthwhile to note before proceeding further that 2-bromo-octane has the same configuration as 2-octanol. Now, the hydrolysis of 2-bromo-octane with the aqueous sodium hydroxide solution follows SN2 mechanism and results in the formation of plus 2-octanol. In view of similar configuration of minus 2-bromo-octane and minus 2-octanol, the configuration of plus 2-octanol must be opposite to that of minus 2-bromo-octane. It is apparent that the OH group occupies a position opposite to that previously occupied by Br, or in other words, the configuration of alcohol is opposite to that of the bromide. Such a reaction in which the configuration of a product is opposite to that of the reactants is said to take place with the inversion of configuration. All SN2 reactions proceed with the complete inversion of configuration. Note: it is not necessary that inversion of configuration in a reaction must be accompanied by a change in the direction of rotation of the new compound formed and vice versa. This may happen in some cases, as in the example of cetidopho, and may not happen in other cases. It may be recalled that two different compounds which rotate the light in the same direction need not necessarily have the same configuration. Factors influencing the occurrence and the rate of the SN2 reaction. The occurrence of SN2 reaction and their relative rates in different cases depend upon the following factors. First, the nature of the alkyl group in the alkyl halide. Steric factors. In order to compare the relative reactivities of the alkyl halides having the same halogen in SN2 reactions, let us first study the effect of the size of the groups attached to the carbon carrying the halogen atom. To understand this, it may be noted that in case of the hydrolysis of methyl bromide, the reactant methyl bromide and the product methyl alcohol contain tetrahedral carbon. But in the transition state, the carbon is bonded to 5 atoms. When the hydrogen atom in methyl bromide are successfully replaced by larger groups such as CS3 and C2H5, there is an increased crowding around the central atom. This gives rise to particularly strong non-bonded interaction in the transition state because of the presence of 5 groups attached to the same carbon. As a result, the energy content of the transition state rises, and so does the activation energy for its formation. Naturally, therefore, the rate of reaction was slow down. It is clear from the above discussion that the relativities of alkyl halide in the SN2 reaction are mainly related to the steric factors retaining the size of the groups. In keeping with this observation, the order of relative reactivities in such reactions is found to be methyl halides, then primary halides, then secondary halides, then tertiary halides. Electronic factors. Let us now have a look at the electronic distribution in the transition state and the reactants in the SN2 reaction involving hydrolysis. In the transition state, there is a partial formation of bond between carbon and hydroxyl ion, which tends to impart a negative charge to carbon. At the same time, there is partial heterolytic cleavage of carbon-halogen bond, which tends to impart a positive charge to the carbon. Since these processes occur simultaneously, the net charge on the carbon in the transition state is practically the same as that in the reactants. Thus, the stability of the transition state and the corresponding reactants would be affected to the same extent by both electron releasing and electron withdrawing substituent. As such, electronic factors have no significant influence on the reactivities of alkyl halides in SN2 reactions. Second one, nature of halogen atom in alkyl halides. Elimination of leaving groups. In SN2 reactions of alkyl halides, the halogen atom ultimately leaves the transition state in the form of a negatively halide ion to form the final product. The more easily the halogen ion is eliminated, the more the rate of reaction. The ease with which the halogen ion is eliminated depends upon its basicity. Weaker the base, the better it would be as a leaving group. Now, the order of increasing basic strength of halide ions is I negative, then Br maximum is fluorine negative, then chlorine negative, then Br negative, then I negative. Therefore, the order of ease of elimination of leaving groups would be I negative maximum, then Br negative, then Cl negative, then F negative. Hence, the order of reactivity of alkyl halides having different halogen is Ri maximum, then Rbr, then Rcl, then Rf. Nature of nucleophilic reagents. Since the transition state in an SN2 reaction is formed by the attack of nucleophilic reagent on alkyl halide, stronger the nucleophilic reagent, more rapid would be SN2 reaction. The decreasing order of strength of a few common molecule nucleophilic reagent is CN negative, maximum, then RO negative, then OH negative, then CH3COO negative, then H2. Fourth one is the nature of a solvent. In a SN2 reaction, the transition state is less polar than the reactants because in the transition state, a negative charge is dispersed over different atoms. Therefore, use of polar solvents helps to solvate the reactants more strongly than the transition state. As such, the polarity of solvents slows down the rate of SN2 reaction to some extent. Now, unimolecular nucleophilic substitution reaction, SN1 reaction, where S denotes substitution and notes nucleophilic and 1 for unimolecular. According to this mechanism, the reaction is considered as taking place in two steps. The first step is a slow and reversible one involving dissociation of alkyl halide to alkyl halide, involving the dissociation of alkyl halide to alkyl carbocation and halidine. The second step is fast one, which involves the reaction between alkyl carbocation and hydroxyl ion to yield an alcohol. Rx reversible process give R plus and X negative. R plus OH negative give rise to ROH, fast reaction. This mechanism required the rate of the reaction should be determined solely by the rate of the first step, which is low step. In other words, the rate at which alcohol is formed should depend upon the concentration of alkyl halide alone and should be independent of the concentration of the hydroxyl ion. That is, R is equals to K into concentration of Rx. It is obvious from the expression above that the reaction follows the first order kinetics. Such nucleophilic substitution reactions which takes place in two stages but the rate determining step involves only one molecule are known as the unimolecular nucleophilic substitution or SN1 reactions. Thus, the alkaline hydrolysis of tertiary butyl bromide takes place through a unimolecular mechanism as depicted below. The reaction is undoubtedly SN1 type as the first step involving only one molecule is the rate determining step and the rate of reaction is proportional to concentration of the tertiary butyl bromide alone according to the above equation. The energy required to break the carbon-bromine bond in the slow rate determining step is applied to the formation of ion dipole interactions between the two kinds of ions and the solvent. Once the carbon-halogen bond is broken, the carbocations formed rapidly combine with hydroxyl ions to yield the alcohol. Here is the energy profile diagram, and from this diagram it may be seen that the reaction involves two transition states. Transition state first is involved in the formation of carbocation intermediate, while transition state second is involved in the combination of carbocation intermediate and OH negative. Since E act for the first transition state is much more than that of the second transition state, it is evident that the formation of carbocation intermediate constitutes the slow rate determining step of the reaction. Rearrangements in SN1 reaction. Reactions taking place by SN1 mechanism frequently give rearranged products. This because these reactions involve carbocation intermediates which are known to rearrange to form more stable carbocation wherever possible. For example, the hydrolysis of 2-bromo-3-methyl-butane through SN1 mechanism leads to the formation of a rearranged product 2-methyl-2-butanol by rearrangement of the intermediate secondary carbocation to tertiary carbocation. SN2 reaction do not give rise to rearranged products as they do not involve the intermediate carbocation. Stereochemistry of SN1 reactions. Let us now consider the stereochemical consequences of SN1 mechanism. The carbocation intermediate formed in the first step of an SN reaction that has a flat structure since the positively charged carbon is in an sp2 hybridized state. Now attachment of the attacking nucleophilic subspecies COH negative to the carbocation step 2 can occur on either face of this flat ion. In reactions involving optically active alkyl halides, attack of the nucleophilic species on one of the face of the carbocation would naturally yield in an enantiomer of the compound formed by attack on the other face. As such, the product obtained should be a racemic modification. The two enantiomers do not take place. In actual practice, however, complete racemization does not take place. This is possible because the nucleophilic species attacks the carbocation even before the departing halide ion has moved sufficiently away from the carbocation. In this position, the negatively charged halide ion shields the carbocation from attack on the front side, the same side as was the halogen. Consequently, attack on the front side, which leads to a product with the same configuration as the reactant, is somewhat hindered. But the same argument attack on the back side, which leads to inversion of configuration, is somewhat occurred. This means that the actual product would no doubt consist of a mixture of enantiomers, but the enantiomer with the inverted configuration would predominate. In other words, the product only would be partially racemized. For instance, the hydrolysis of -2 bromoactane under conditions where concentration of OH negative ions is low follows SN1 mechanism and yields a partially racemized product. Factors influencing the occurrence and the rates of SN1 reactions. The main factors which influence the occurrence of SN1 reaction and their relative takes in the different cases are as follows. First, the nature of alkyl groups in the alkyl halides. Electronic factors. The rate determining step of an SN1 reaction is the formation of a carbocation. Therefore, the relative reactivities of alkyl halides may be expected to be the same as the order of ease of formation and relative stabilities of carbocation. This is indeed found to be so. In keeping with the known order of relative stability of carbocations, the order of relative reactivities of alkyl halides is found to be tertiary halides, secondary halides, primary halides, and then methyl halides. Thus, unlike SN2 reaction, the relative reactivity of alkyl halides in SN1 reaction are mainly determined by the electronic factors which affect the stability of carbocation and not by steric factors. Second one, nature of halogen atom in alkyl halide. Ease of elimination of leaving group. In SN1 reaction, the formation of carbocation, which is the rate determining step of the reaction, involves the elimination of halide ions. It is quite understandable that the better the leaving group, the more the easily the carbocation will be formed, as the order of ease of elimination of leaving group is maximum I negative, then Br negative, then Cl negative, then F negative. The order of reactivity of alkyl halides having different halogens is maximum Ri, then Rbr, then Rcl, then Rf. It may be pointed out that with respect to halogen, the order of reactivity of alkyl halide is the same in both SN2 and SN1 reaction. Third one is the nature of nucleophilic reagents. Since the nucleophilic reagent is not involved in the rate of the determining step of SN1 reaction, its nature does not influence the rate of reaction. Nature of the solvent. Nature of the solvent plays a very important role in the occurrence of SN1 reactions. This is because polarity of the solvent is crucial to the ease of formation of carbocation from alkyl halides. In case of SN1 reaction, ionization of an alkyl halide takes place only because of almost the whole of energy required to reach the transition state during ionization is supplied by the formation of dipole-dipole bonds between the solvent and the polar transition state. It is obvious that the higher the polarity of solvent, the stronger the solvation forces and the faster the ionization energy. Comparative survey of SN2 and SN1 reaction. It is clear from the following discussion that while primary alkyl halides generally react by an SN2 mechanism, tertiary alkyl halides generally follow SN1 reaction mechanism. Secondary alkyl halides can react by both mechanisms. However, it must be noted that the reaction pathway can be varied by changing the other reaction conditions as summed up below. First, the nature of the nucleophilic reagent. The nature of nucleophilic reagent is an important factor in determining the actual mechanism of reaction. Generally speaking, strongly nucleophilic reagents favor SN2 mechanism since they can push halogen away from the molecule of alkyl halide. On the other hand, weak nucleophilic reagents tend to favor SN1 mechanism as it is easier for them to attack the carbocation already formed. Second one, concentration of the nucleophilic reagent. It is quite reasonable to expect that high concentration of the nucleophilic reagent would favor SN2 mechanism while low concentration would favor SN1 mechanism. This is found to be so in actual practice. Third one is the nature of the solvent. The nature of the solvent plays a very important role in determining the mechanism by which a reaction occurs. This is because polarity of the solvent is crucial to the ease of formation of carbocation from alkyl halides in SN1 reaction. Therefore, as already explained above, solvents of high polarity favor SN1 mechanism while solvents of low polarity favor SN2 mechanism. Depending upon the factors listed above, the reaction may proceed by SN1 or SN2 mechanism. Which mechanism operates in a particular case can be ascertained on the basis of the kinetic study of the reaction. Elimination reactions, E2 and E1 mechanism. While discussing the mechanism of dehydrohalogenation or typical elimination reactions of alkyl halide, it was stated that the reaction takes place by a single-step bimolecular process. It should, however, be noted that this is not the only possible mechanism of elimination reaction of alkyl halides. Like the nucleophilic substitution reaction, the elimination reaction of alkyl halides may also follow two different mechanisms. These two mechanisms, called the E2 and the E1 mechanism, are rather closely related to SN2 and SN1 mechanism of substitution. The E2 mechanism. This mechanism involves a single-step bimolecular elimination process. It is assumed that the attacking base removes a proton from a beta carbon with the simultaneous loss of halide ion from the alpha carbon and the formation of an additional bond between the two carbons. The reaction obviously follows the second-order kinetics, and the rate of reaction depends upon the concentration of both hydroxyl ion and the alkyl halides. Structural factors. Structural influences on E2 reactions have been carefully investigated. For a given alkyl group, the rate of elimination varies with the nature of halogen in the order of Ri, then Rbr, then Rcl, then Rf in the decreasing order. For a given halogen, the ease of elimination follows the order maximum tertiary halide, then secondary, then primary halides. Unlike SN2 reaction, E2 reactions are not appreciably influenced by steric factors and take place easily with tertiary halides. The E2 reactions are, however, generally brought about the rather strong bases. In case of alkyl halides having the unsymmetrically R groups like tertiary amyl chloride, it is possible to have two or more different alkenes formed depending upon which beta hydrogen is removed by attacking base. Generally speaking, E2 elimination reactions tend to yield the most stable alkene, which is usually the most highly substituted. For example, tertiary amyl chloride. E1 mechanism. This mechanism operates through a two-step process in which the rate determining step involving only one molecule. It is believed that in the first step, which is a slow rate determining step, the alkyl halide dissociates into halide ion and carbocation as in SN1 reaction. In the second step, which is a fast one, the carbocation loses a proton to the base and forms the alkene. The complete mechanism may be depicted as given. It is obvious that the reaction follows the first order kinetics as the rate determining step involves only one molecule. The rate of the reaction is independent of the concentration of base and varies only with the concentration of alkyl halide. Many secondary and tertiary alkyl halides undergo E1 type of elimination in solution of low base concentration. Structural factors. Structural influences of E1 reactions are similar to those for the SN1 reactions. For a given alkyl group, the order of reactivities of different alkyl halides is maximum Ri, then Rbr, then Rcl, then Rf. For the same halogen, the ease of elimination is in the order of maximum tertiary halide, then secondary halide, then primary halide. It should be noted that unlike SN2 and SN1 reaction, the order of reactivities of alkyl halides in both E2 and E1 reactions is the same. Like E2 elimination, E1 elimination also tend to favor the formation of the most stable or highly substituted alkene. In case of alkyl halides, per elimination can take place in more than one direction. Thank you.